Howdy, folks. Let us get back to learning more about the electron. We're in Unit 3 now, and we're moving into really the heart of Unit 3, and that is our discussion about quantum numbers. So let's get started right away. Here we go. Consider the principal quantum number. What's that? Principal quantum number. What is its symbol? And what does it mean for the electron, and what are its possible values? Okay, I think we need some notes, right? Good. So let us start over here. Let's say quantum numbers. Well, I think the place to begin, oops, sorry. Oops. I think the place to begin with quantum numbers is first of all, who cares? Why should we care about this? And so what I want to know is, what's the purpose? What are we trying to achieve with quantum numbers? Well, the purpose is really, I think, that we're trying to characterize every electron in an atom. Good. Now, how are we going to do that? And we're going to do this by determining the number one, the energy level, the shape, and the orientation of the orbital. And remember, what's an orbital? It's just a most probable location of the electron. So we're going to characterize every electron in an atom. How? By determining the energy level, the shape, and orientation of the orbital, and by determining the spin of the electron. By doing these four things, we uniquely characterize an electron in an atom. Good. So now, that's kind of the purpose, the reason why. Now let's kind of go over here and discuss the quantum numbers. So what are our, I guess, types, we'll call them the types of quantum numbers. Or, not types, it's the big four. What are the big four, the four quantum numbers? I guess that's better. Ooh, I kind of like that red. The four quantum numbers. Now we're going to need a lot of space, folks. So on your paper, make sure you have a lot of space. Here we go. I'm going to take this over here, and we're going to start with the first of the four quantum numbers, and that is what we call the principal, right? Principal meaning the main quantum number. That's our first quantum number. Yoink, and we'll keep him in red. And then we'll go and we will learn something about something called the angular momentum quantum number. I'm just going to go with Q number. Good. And then we'll go with some green for the magnetic quantum number. And finally, we will use some blue to talk about our last quantum number, and it is called the spin quantum number. All right? So these are the four quantum numbers, and we want to learn a little bit about each. And the first thing we want to understand is, what are their symbols? The symbol for the principal quantum number is N. The symbol for the angular momentum quantum number is L. The symbol for the magnetic quantum number is, believe it or not, M. And for my spin quantum number is S. Okay, so we have our symbols, we have our names. Now, what do they mean? What's the importance of them? And we're going to need more space here because there's big importance with the principal quantum number. What is its meaning? It means it represents the energy level. The energy level of the orbital or for the electron. And another way to think about the energy level is it also represents the distance from the nucleus. for the electron. The higher the energy level, the farther from the nucleus, okay? And so that's what we mean by that's what's the importance of the principal quantum number. So if I have a quantum number at 6 and a quantum number at 10, what's the difference between those electrons, between the electron at 6 and the electron at 10? Well, the electron at 10 has a higher energy. It's at a higher energy level, and that also means it is farther from the nucleus. Good. And finally, we want to ask ourselves, hey, what are my possible values? The possible values for the principal quantum number are all positive integers, starting at 1. Starting at 1. Uno, eins, zwei, drei, vier, fünf, right? And so forth. Good. All right. I think we can answer our question. Let's look at this. Consider the principal quantum number. What is its symbol? Hey, I know that. It is N. Good. What does it mean for an electron? It represents the energy level of the electron. And it can also represent then too what? The distance from the nucleus for the electron. Cool. And finally, what are its possible values? Hey, it can be any positive, what? Integer. Positive integer, right? Good. It can be any positive integer. So that means it can be 1, 2, 3, 4, 5, so forth and on into infinity. Or no, to infinity and beyond. How's that? Cool. Great. Moving on. An electron in the n equals 2, okay, that means the electron in the n equals 2, and an electron in the n equals 4 energy level, which has a higher energy. Okay, we talked about that just a second ago, right? We said that the n represents the energy, right? And so if I am at n equals 4, that means I have more energy than at n equals 2. So n equals 4 has more energy than n equals 2. And which is farther from the nucleus? We talked about that too, right? That means at the higher energy level, I am farther from the nucleus. And the way to think about that, right, is here's my nucleus, and here's an energy level, energy level, energy level, energy level, right? N equals 1, N equals 2, N equals 3, N equals 4. The farther I go, the higher my energy level is, and the farther I am from my nucleus, right? When I'm at the N equals 4, I am this far from my nucleus, for instance, and 2, I am this far. Which one has a higher energy? This is the higher, yikes, this is the higher, let's try to spell right, energy. And you'll notice as we increase our energy level, my distance from nucleus increases, right? Distance increases. Good. So the n equals 4 electron at n equals 4 is farther from the nucleus than the electron at n equals 2. Great. Next. Consider the 5th energy level. What shell is this? Shell. Wait. Did we talk at all about shell yet? I don't think so. And how many orbitals can exist? How am I going to know this? Well, you know what? There's some cool stuff that N tells us that I've kept secret from you so far. So let's learn some more stuff. And let's write down here cool stuff within. Cool stuff within. Okay, not cool stuff within, but cool stuff with N, right? First thing is that N represents my shell. What's a shell? Well, a shell is a collection of all orbitals at a given energy level. Okay, now I'm giving you some code words here. From now on, whenever you see these two words together, energy level, you should always start thinking in. Okay? So really we're saying, hey, a shell is a collection of all the orbitals at a given n. Cool. So when I talk about, hey, I'm at the fourth shell, that means I'm at the fourth energy level, and that means I'm talking about all the orbitals that are within that energy level. Good. Well, there's a way also that we can relate n to the number of orbitals, and that is n squared. N squared represents the number of orbitals that can exist at a given energy level. Energy level. So what do I mean by that? Let's say we are at the n equals 2 energy level, right? Well, how many orbitals can exist? Well, n squared. So that means I could have n squared. That means I could have n squared orbitals. 2 squared is equal to 4. So there are 4 orbitals which can exist at the n equals 2 energy level. And finally, a last cool thing about n is I can actually figure out, because of the Pauli exclusion principle, the number of electrons. Number of electrons that can exist at a given energy level, right? Sure I can. If I know the number of orbitals is n squared, and there can be no more than 2 electrons per orbital, then 2n squared is equal to the number of electrons at a given energy level. So, once again, if I'm at n equals 2, then I have how many electrons that can exist at can occupy, I guess I should say, the second energy level? 2 squared. So 2 times 2 is 2, is 4 times 2 is 8. 8! So 8 electrons can possibly occupy the second energy level. Got it? Okay, let's go back and answer our question. So, consider the fifth energy level. Yeah, got that. What shell is this? Well, we said that the N represents the shell, so this would be the fifth shell. Good. How many orbitals can exist? We said, hey, orbitals can be represented or can be found out by taking n and squaring it. I'm at n equals 5, so 5 squared is equal to 25 orbitals can exist at the fifth energy level. And I cannot overemphasize this because sometimes our wording here gets a little misleading. What is an orbital? It's the most probable location of an electron. It is not a track. It is not a shoebox. It's really nothing that exists in three-dimensional space. It is nothing but a probability, right? And I know that's really difficult to understand. It's hard for me to understand when we use words like that, okay? But what we're saying is there are 25 different high probability locations where an electron is likely to be found at the fifth energy level. Phew, that's hard to say, isn't it? All right, let's see what you can do on your own. Consider the third shell. How many electrons can exist in this shell? How many orbitals can exist in this shell? All right, turn me off here, and when you're done, call me back. All right, I'm back, and let's get some answers. I'm in the third shell. Third shell means n is equal to 3, right? How many electrons? Well, can exist in this shell? Well, what do we know? N squared is the number of orbitals. 2n squared is the number of electrons that can exist or can occupy this shell. And so I'd have what? 2, 3 squared. 3 squared is 9 times 2 is equal to 18 electrons can occupy the third shell. How many orbitals can exist in this shell? Ah, that's easy. We know that already. Orbitals are represent the number of orbitals are represented by n squared. And so that means I have n. N is 3. 3 squared is equal to 9. 9 orbitals exist in the third shell. Great. All right, I think this is a good place to stop. We've really covered everything we need to know about the principal quantum number. Next time you see me, we will talk about the angular momentum quantum number. Enjoy. Ciao.